In this problem, we are looking at tensile stress. And a couple things we want to make note of. Number one, over here on the right, you can see that this megapascals, 1 Pascal is 1 Newton over 1 meter squared. A megapascal is a Newton over a millimeter squared. Also, this equation, this is a sigma, a lowercase sigma, and that's stress. So stress T, that's tensile stress we're looking at here. P is our external load, and A is our cross-sectional area in this case. So for this problem, this is a steel rod with a cross-sectional area of 50 millimeters squared. It's subjected to a tensile force of 1,000 newtons. Calculate the tensile stress in the rod. So we are given our force, or external load, is 1,000 newtons, and our area here is 50 millimeters squared, and we're just using our straightforward equation here. Sigma T equals P over A. Sigma T equals 1,000 divided by 50, and this is Newton over millimeters squared, and that will give us an answer of 20, and this will be in megapascals. And that's our tensile stress for that problem. In the next problem, it says a 2-meter long steel rod has a cross-sectional area of 0.3 centimeters squared. The rod is part of a vertical support that holds a heavy 550 kilogram platform that hangs attached to the rod's lower end. Ignoring the weight of the rod, what is the tensile stress in the rod? So for this problem, we have a cross-sectional area of 0.3 centimeters squared. So we got to change that into meters squared or millimeters squared, depending on if you want it in pascals or megapascals. We'll just put it in pascals. So area equals 0.30 centimeters squared. And to convert that, there's 100 centimeters in 1 meter. So there's 100 square centimeters in 1 meter squared. So that's 0.3 divided by 100 squared, which comes out to be 3 times 10 to the minus 5th meters squared. And here you can see we have a mass, 550 kilograms. So what happens here is if our mass is 550 kilograms, the weight of this mass is what's causing our force. So the force is equal to the mass times the gravity. So that would be 550 times 9.8. And that's how we get it into newtons. So that's 5,390 newtons. So we've changed our area into meters squared, our force into newtons, and we're looking for tensile stress here. So sigma T equals P over A. Sigma T equals 5,390 newtons over 3 times 10 to the minus 5th meters squared. Sigma T equals 1.80 times 10 to the 8th pascals. So a megapascal, just to let you know, there's 1 times 10 to the 6 pascals in 1 megapascal. So that would be 180 megapascals. So that would be the tensile stress in our rod. We didn't need the length of the rod in this case. Our third problem, a mild steel rod, 2 meters long and 3 centimeters in diameter, is subjected to an axial pull of 10 kilonewtons. Find the stress in the rod. In this problem, we're going to look for our area formula, pi over 4d squared, which is the same as pi r squared, except that radius is d over 2. So, right, d over 2 squared equals r squared. So that gives us d squared over 4. And that's where this equation here comes from, that pi over 4d squared. And it says a mild steel rod, 2 meters long and 3 centimeters in diameter, is subjected to an axial pull of 10,000 kilonewtons. Find the stress in the rod. I guess we'll put our answer in, we'll go with, let's go to megapascals. We'll do it in megapascals. So this would be 1 millimeter squared. So 1 Newton over 1 millimeter squared. That's a megapascal, if you remember. So we'll go to this problem, and it's looking for the stress again. We know that the diameter is 3 centimeters, so we're going to change that into millimeters. 1 centimeter has 10 millimeters in it, so that's 30 millimeters for our diameter. And our force here is 10,000 kilonewtons, which there's 1,000. Oops, got that backwards. Well, that erased the whole page. Let's just start that over again. I want to change pen color anyway. I don't really like the red. So we're doing 1 Newton over 1 millimeter squared is a megapascal. And hopefully you got that stuff with the diameter down here, right? So we can also use A equals pi r squared if we're looking for the radius. But anyway, this isn't even the same problem. Here it is. My bad. So we go back to this problem here, and I guess I'll stay in red while I'm here. 1 kilonewton has 1,000 newtons in it, so that's 10,000 newtons. And our goal in this problem is find the stress, so sigma T equals P over A. Sigma T equals 10,000 newtons over pi over 4 times 30 squared. Now when you put this in your calculator, make sure that you're putting the correct brackets in the denominator. So when you go to find sigma T and you take 10,000, you want to make sure that you're not doing 10,000 divided by pi times 4, or divided by 4 times 30 squared, and you're not doing them and just putting them straight into your calculator and getting the wrong answer, because that will be an order and operations problem. So what you need to do is make sure that you're doing this, right? 10,000 divided by open bracket, pi over 4 times 30 squared, close bracket. If you just put it in like this, 10,000 divided by pi divided by 4 times 30 squared, you're going to get a different answer, because it's going to do it in the order of operations. So it's going to take all this and then multiply the whole thing by 30 squared, and it's going to give you a huge number, way different than what you should have. And what you should have here is once I get this typed into my calculator, 14.15 megapascals. That's what that answer comes out to be. 14.15 megapascals. If you do it this way, that's what you get. If you do it this way, you get a way different number. It would be 10,000. Let's just put it in here and see what we get. Pi divided by 4 divided by 900 times. You would get 7.16 times 10 to the 5th megapascals, which is way different. So make sure that you're putting it into your calculator correctly, using the correct parentheses. And now we're back to this problem that I screwed up. So let's just start this one fresh. And we are going to switch it over to the blue just for fun. It says a rod 2 meters long is subjected to an axial tensile pull of 30 kilonewtons. Find the minimum diameter of the rod if the permissible stress is 200 times 10 to the 6 pascals. And a Newton over a meter squared is a pascal. So here we have an axial pull of 30 kilonewtons, and I'm just going to go right ahead, since we already did that in the last problem, and change it into newtons. We're looking for diameter this time, and we know that our stress is 200 times 10 to the 6 newtons over meters squared. So this time we're going to have to do a little algebra. Sigma T equals P over A. Cross multiply, right? We're just going to cross multiply those. A equals P over sigma T. A is pi over 4 D squared is equal to P over sigma T. So that means D squared equals 4P over pi times sigma T. So we'll put this in. So that'd be 4 times 30,000 over pi times 200. 200 times 10 to the 6. And that gives me a diameter squared of 1.91 times 10 to the minus 4th. So that would be meters squared. And we want to take the square root of that to get D. So D then equals 1.38 times 10 to the minus 2nd meters. Or 1.38 centimeters. Next one. A hollow cylinder, 1.5 meters long, has an outside diameter of 45 millimeters and an inside diameter of 25 millimeters. If the cylinder is carrying a load of 20 kilonewtons, find the stress in the cylinder. So the cylinder, right, has an outside diameter and an inside diameter. We're just concerned about the area of the material. So what we're going to do is define the diameter, or define the area, I should say, not the diameter, I'm sorry. Define the area. The area in question is going to be pi over 4 times outside diameter squared minus inside diameter squared. That's how we find the area here. This is a lot different than area equals pi over 4 outside diameter minus inside diameter squared. That is incorrect, because essentially this is just area outside minus area inside, and we factored out the pi over 4. That's how we came up with this equation right here. This one is bad and will get you the wrong answer, so don't use that. In this case, we know that the outside diameter is 45, so our outside diameter is 45 millimeters. Our inside diameter is 25 millimeters. And the load, P, is 20,000 newtons, and we're looking for the stress, and we'll just do this in megapascal since it's in millimeters. So sigma T equals P over A. Sigma T equals 20,000 over pi over 4 times 45 squared minus 25 squared. And this is going to be one of those calculator situations where you may take a couple times to get this into your calculator correctly. So we take 20,000, we divide it by pi over 4, and then we divide it by 45 squared minus 25 squared. And that gives me an answer of 18.19 megapascals. That's what their final answer comes out to be. So make sure you can put that in your calculator correctly. It took me 2 times to get it in my calculator correctly, so it may take you more than that. Or maybe you got it on the first try, so that would be good as well. Those are our simple stress problems, our tensile stress problems. We are going to look at a couple more difficult applications here. So let's move forward. Still looking at our tensile stress. This one says a homogeneous 3,924 Newton bar AB is supported at either end by a cable as shown. Calculate the smallest area of each cable if the stress is not to exceed 90 megapascals in the bronze and 120 megapascals in the steel. So the first thing we have to do is find the force in these cables. And you can see we have a parallel force system in equilibrium here. And we can also see that we know the weight of the bar. So the weight of the bar is right here, and that is 3,924 newtons. We can see that from here to here, it's 5 meters on each side. So we can find the force in both cables. We can use the sum of the moments about A. Set that equal to 0. That gives me 3,924 times 5 plus B times 10 equals 0. B equals 1962 newtons. Then we can do the sum of the forces in the y, set those equal to 0. A minus 3,924 plus 1962 equals 0. A also equals 1962 newtons. Pretty easy with the regular distances or the equal distances on both sides. But we learned how to do that. Now we know the force in each one. From this force, we can determine the stress in each, or we know the stress in each one. We know the stress, the maximal allowable stress in the steel is 120. So I'm just going to call it theta S for the steel, 120 megapascals, and theta B for the bronze, that's an S. I know it's hard to see. Kind of right on top of myself there. That's an S. Is 90 megapascals. Our goal here is to find the smallest area of each cable. So we just use our formula here to find area. I'm just going to rearrange. I'm just going to cross multiply. Area equals P over sigma. So for the steel, area of the steel is equal to 1962 over 120. Area of the steel is 16.35 millimeters squared. And I'll use the same formula for the bronze. Area of the bronze, same number. $21.80. So that's a fun problem because we get to use our previous skills in it. It'd be even more fun if it had some extra forces on there, make our original part a little bit more challenging, but that's how you would solve that problem. The next problem is a problem where now we have a force P essentially, and according to Newton's third law, whatever that P is on one side of this is going to be on the other side. So when we look at this, we're only looking at P on one portion, right? We're not going to double the P value. The P is still going to be the 400. So in this case, because it is a reaction, so it says consider the following non-uniform cross sections in AB, BC, and CD having cross-sectional areas of A1 is 10 inches squared, so that'd be 10 inches squared. Area 2 is 22 inches squared. and area 3 is 35 inches squared. So those are our three cross-sectional areas of our three shapes. And it wants to know, what is the tensile stress in each section? So to find the tensile stress in each section, essentially we're just going to take the P, the 400, and divide it up over its section, because what happens here in section A1, right, you're going to have P pulling this way, and that equal opposite P is going to be pulling that way. And then in section 2, you're going to have a P here and a P here, and then in section 3, you'll have that P and that P. So the P's all equal out. We're not adding additional forces here. It's just going to be the 400. So to find our stress in portion 1, we would just take 400 over 10. So that would be 40. And it looks like we're in PSI here. Section 2 would be 400 over 22. That would give me 18.18 PSI. And in section 3 would be 400 over 35. Put that in your calculator correctly, and you get 11.43. So here we're using PSI, which is fine. That's pounds per square inch for our stress. And that's that problem. I guess we could circle these and move on. In this problem, we pretty much have the same situation, except we're not given our areas. We have to actually solve the areas out with the pi d squared over 4. What do we have? 15 kilonewtons. So this is 15,000 newtons. And we can leave our areas in millimeters, and that will, our diameters here, these are diameters. This is our diameter. That's what that means. We're not really cared about the length. And we can leave our diameter in millimeters, and that will give us our answers in pascals. So we'll use our pi over 4d squared formula. So sigma for 1 is going to be 15,000, right? Our formula is sigma equals P over A. I don't want to get too excited and not write the formula. So that's 15,000 divided by pi over 4 times 40 squared. Sigma 1 is, or we can call it sigma AB, whatever you want to call it. Right, we can call it sigma AB. That's probably more proper. For that section, sigma AB is 11.9 megapascals. Sigma BC is 15,000 again, over pi over 4 times 15 squared. So here we have a smaller cross section. We would assume that has a bigger stress, 84.8 megapascals. And sigma CD would be 15,000 over pi over 4 times 30 squared. Sigma CD would be 21.22 megapascals. I was going to write newtons per meter squared, but millimeters squared, but it's better to write megapascals. And those are our three. No big whoop there. Now we're going to take this principle and we're going to add some forces. So here in this case, it says an aluminum rod is rigidly attached between a steel rod and a bronze rod as shown. Axial loads are applied at the positions indicated. Find the maximum value of P that will not exceed the stress in steel of 140 megapascals, in aluminum of 90 megapascals, or in bronze of 100 megapascals. So what we're doing here is we're looking at each one of these three sections. And we'll start with the bronze section. And you can see in our bronze section, excuse me, in our bronze section, what's actually happening here is that this force 2P is pushing on all three of these sections, right? It's pushing on this section, it's pushing on this section, and it's pushing on this section. And all of these sections are going to be pushing back. So what we're going to do is we're going to isolate each of the three sections, right? We're going to isolate here, we're going to isolate here, and we're going to isolate here. And what we're going to do is try to figure out what's actually happening at the back of this section. So if we're pushing here with 2P for our first section, what's happening back here is that 2P is pushing back. This P is not acting on the bronze, it's acting on the aluminum. So for our P for the bronze, it's actually going to be 2P. For the aluminum, and I'll write it down here so it makes a little more sense. We actually have a net 2P going in this direction. For the aluminum, right? For the aluminum, what happens is if I erase this, and now we're looking at the aluminum, let me put a little divider in here so you know where I'm talking about, from there to there. Now I'm looking at the aluminum. So I have 2P pushing, 1P is countering that 2P. So my net force here is 2P minus P. So from that section to that section, I have 1P going to the left. And in my final section, if I come to the steel, right? If I come to the steel, now I have 2P, P, and then 4P. So I have 6P going this way. I have 1P going this way. So that gives me a net 5P going to the left for the steel. So each one of these different sections has a different amount of force reacting to the forces on the right. So the reaction is coming back. So we can see there's a compression. So to use this data, we want to figure out what P is for each of the areas. It says for an aluminum rigid rod is rigidly attached between a steel rod and a bronze rod as shown. Axial loader is applied at the positions indicated. Find the maximum value of P that will not exceed, that's key, a stress of 140 in the aluminum, 90 in the bronze, and 100 in megapascals. So we want to find this P. Our lowest P is going to be our maximum, because if we go greater than that, it's going to break the segment off that it can't withstand. So we're going to find P for each section. So we're going to rearrange our equation here. And I switch back to red for some reason. I find red to be a little bit much. So if I'm looking for P equals sigma T times A. That's our formula. I'm not really cross multiplying. I'm just moving that up. Multiplying both sides by A, I guess you could say. Now, we'll do first for bronze. P for bronze is equal to 2P. We have two P's here for bronze. 2P for bronze is equal to sigma T, actually compression in this case, so let me just change that T to a C. That'll be exciting. Something new. Sigma C times A. So for bronze, we get 2P equals, I want to rewrite this. I don't like how I wrote it. Oh boy. Let's go back here. Big eraser. P for bronze equals sigma CA. P for bronze is equal to 2P. So 2P equals sigma C, which I should have written down, but I just didn't. 100 megapascals times the area, 200 meters squared. So P in this case is equal to 10,000 kilonewtons when you put that in your calculator. You follow me? So the generic equation PB, we're looking for the force for bronze, PB, equals our maximum stress for compression. I could probably call this B for bronze, that might make more sense, times the area of bronze, which I got right here. So the maximum PB. Now, for aluminum, that's PA, that's equal to 1P. See, we got 1P actually acting on the aluminum. So when I do PA, sigma A, AA, PA is just 1P. So I just write P in there. Sigma A, so for the aluminum is 90 times AA, 400. What's that, 36,000 newtons? That's for aluminum. And then for the steel, PS is going to equal sigma S, AS. Well, PS is equal to 5P. So 5P, that's 140 times 500. So P in this case is 14,000 newtons. This is newtons, not kilonewtons. Got all carried away there. Just newtons. 14,000 newtons. That'd be 10 kilonewtons. So you can see the question asks, find the maximum value of P that will not exceed a stress. The bronze, the 10,000, the 10K, this is our lowest amount of force we can apply. If we apply 14,000 or 36,000, this is going to buckle and break. It's going to be stressed out. So we can only apply 10,000 kilonewtons to this situation. That is our last tensile or stress problem. So I will make a new recording for bearing and shear stress. So we're stopping here.